you very much, Mark, for organizing such an interesting meeting, and to all the speakers who made it interesting as well. Also, the first talk was really fun, so thank you. So I'm going to talk about pathogen interactions. So you all know that the influenza virus spread in the air, and when the virus finds a new host, it can bind to the surface of the epithelium cells in the human. But the transmission capacity of the influenza and its virulence can be influenced by several factors. So it can be the external environment, such as the condition that will allow for transmission, temperature, humidity, contacts. Also the immunity of the host, the drug exposure of the patient or the human, and lastly, the co-circulating pathogens, so the co-inhabitants within the nose or the throat. Because influenza is not a solo sailor, and there are many co-inhabitants for influenza within the nasal cavity, nasopharynx, or oropharynx. There are lots of bacteria, commensal bacteria, Streptococcus pneumoniae, Staphylococcus aureus, Haemophilus influenzae, Neisseria meningitis, M. cataralis. And there are also lots of respiratory viruses that occupy the same niche, RSV, rhinoviruses, adenoviruses, coronaviruses, parainfluenza. The interaction between influenza and others has been suggested for a long time because it's well known that in the past pandemics and also in seasonal epidemics, most fatalities from influenza are actually due to secondary bacterial infection from several bacteria. And the evidence of interaction has come from animal models, which have shown that the influenza infection can predispose to bacterial colonization or bacterial infection. So here I'd like to introduce, so I'm talking about interaction, but it's actually a very old concept in ecology, and this is combined in the theory of the concept of metabiosis. So it's the relationship whereas one organism can create conditions that are favorable for a second organism. So there are different types of relationship. The commensalism, so this one is the one where I eat my cheese and I drink my wine, and you drink your wine and you eat your cheese, and we are happy like that. The second one is the mutualism, so I share my cheese and you share your wine, for example. And the third one is the parasitism, so I eat my cheese and I eat your cheese because I want more, and you don't have any more cheese. So the parasitism can be seen as a competition between organisms, and the mutualism can be seen as a synergistic relationship between the organisms. So it's very impressive when you have a look at literature. So here I've written a non-exhaustive list of the suggested interaction with influenza, and actually mainly, I think nearly all the bacteria and viruses I've mentioned before that are there have been suggested as potential interaction with influenza. So lots of bacteria. And also lots of respiratory viruses, and also even some bacteria from the gut. And there are some positive interactions, so synergistic interactions, and also some negative interactions that have been suggested. So regarding the biological mechanism, some mechanisms are more on the short term, and others are more on the long term. So for the short term, the infection with the influenza virus has been suggested to cause some damage on the epithelial cells of the human, of the nasopharynx, and then to enhance some the bacterial adhesion, and also to facilitate the tissue invasion of the bacteria. So this is, for example, the mechanism that has been suggested for the positive interaction between pneumococci and influenza. Some mechanism also of interaction through the host innate immunity. For bacteria, for example, the virus has been suggested to modify, inhibit, or deactivate the immune response against the bacteria, and that could be another reason of the synergistic interaction. And also, some viruses have been suggested to modify the interferon-induced antiviral state, and that's the mechanism that has been suggested for the negative interaction between rhinoviruses and influenza, because you usually don't see outbreaks of rhinoviruses and influenza together. The last mechanism that has been suggested is the co-transmission. So, for example, when you are infected with the influenza and you have some symptoms related to influenza, you're sneezing, you're coughing, you're transmitting your influenza in the air, but you're also transmitting more, maybe the bacteria you have here. And so you increase the transmission of another pathogen. So the last mechanism is a long-term one, so it's through the host-specific immunity, and that's typically the example of the cross-immunity between influenza subtypes. So you are infected with influenza, and you develop some immunity that can protect partially or completely to other viruses. So what's the impact in terms of public health? So here, let's say that we have two pathogens, P1 and P2, and P1 is already there, so it's already settled in the population. And P1 and P2 are interacting, so they can have a synergistic interaction. P1 facilitates P2, or they can have neutral, nothing, or they can have also some deleterious interaction, so they are in competition. If P1 is there, then P2 has less chance to invade. So what happens now? So first, when we have a synergistic interaction, then the fitness of P2 is increased, because P1 is increasing the chance of P2 to invade. On the contrary, when we have a competitive interaction, the fitness of the P2, of the second pathogen, is decreased. So now, what's happening when we try to control for against P1? Okay, so we are trying to control P1, and so we reduce infection with P1. So if we are in the case of synergistic interaction, we control P1, and then we are going to reduce the susceptible pool for P2. So we are likely to reduce the number of infections with P2. On the contrary, if the interaction is negative, if it's deleterious, if we increase the control of P1 and we reduce the infection with P1, then we are going to increase the susceptible pool for P2, and so we might increase the infection with P2. So controlling influenza can affect the dynamics of other circulating pathogens and lead to beneficial or detrimental outcome. So considering interactions when we try to control influenza could lead to better evaluation and anticipation of the effects of this control measure. So there are big challenges here. First, we need to get a better knowledge of interactions. We need to identify which are the interactions actually occurring. We have to evaluate their strengths, and we have also to evaluate their burden. What is the excess cases that is due to this interaction? And then we need to predict the overall effect of control measures by taking into consideration this microbiota, let's say, but we can be less, we can just have a look at some pathogenic microorganism. So all this requires mechanistic modeling. Okay, so what has been done in terms of modeling for interaction? Actually, not much. So the interaction is a very important question in ecology, and there is a large quantity of generic model, more theoretical, that come from the ecology. And for example, for multi-strains model, there are lots of very interesting studies. But we have a look at models that are actually applied to influenza. They are not really many. So interaction between influenza and other viruses, I've been looking for them and I've not found any, so maybe I missed some, but yeah, they are not obvious. So there is a very interesting study recent from last year in PNAS that actually developed some mathematical models of the co-circulation of paramyxoviruses and assess the cross-immunity, but there is no inclusion of influenza there, obviously, and so that's the only model I could find for interaction, co-circulation of respiratory viruses. Then for the interaction between influenza and bacteria, there is one model, one biological model that has been studied by mathematical models, is the influenza pneumococcus model. And actually before 2013 there was nothing, and in 2013 there were 4 modeling studies on pneumococcus influenza that were published. So this is the most studied interaction model, and the interaction between influenza and pneumococcal has been suggested for a long time now. So it's also maybe the older model. So the pathophysiological interaction between flu and pneumococci has been suggested to be mostly an effect on the virus on the bacteria, that the virus could impact the evasive potential of the bacteria, and also the virus can impact the colonization with the bacteria. It could be on transmission, what I was saying before, or on acquisition, so the susceptibility of the host. So there is a strong signal of interaction in experimental studies, but the results are inconsistent in human population studies from surveillance data, from regression and correlation analysis. So the question was, what can mechanistic models say about that? So there are 2 within-host kinetic models of influenza infection. The one by Smith and colleagues and the one by Shrestha and colleagues. And there are 2 different population models of interaction between flu or respiratory viruses and pneumococci or pneumonia. So I'm going to present some of these models. I'm going to start with a within-host model of interaction between influenza and pneumococcus. So that's the model that was proposed by Smith and colleagues. So it's a very interesting study because they carried out some experiments on mice which were infected with the virus and then with the bacteria. And then they developed a kinetic model of pneumococcal growth and influenza virus growth to test different interaction mechanisms between the 2 species. And by the fitting, they try to select some mechanism that would be more plausible. So there are 2 mechanisms that relate to an effect of the bacteria on the virus, and 2 mechanisms that relate on the effect of a virus on the bacteria. So, for example, the bacteria can increase the production of the virus, and the virus can decrease the immunity response against the bacteria or increase the carriage capacity of the bacteria. So they concluded that by fitting their model to the experimental data, they concluded that the 2 main mechanisms that looked more realistic regarding their model and the data on the mice was that the impact of the influenza on pneumococci was through immunity. So the virus would decrease the destruction of the bacteria, and also there was an effect of the bacteria that would increase the virus production. So that's a mutual synergistic relationship. So the second study I'd like to present is again a kinetic model by Shrestha and colleagues. And they try to predict the clinical outcome after antiviral treatment. So they simulated again the growth of the bacteria and the growth of the virus. So first here you have, according to different level of pneumococcal inoculum, the clinical outcome. So for low pneumococcal inoculum, you have immediate clearance of the bacteria. For medium inoculum, let's say there is eventual clearance, and for high inoculum, you have invasion. So this is without influenza. But then when the mice, let's say, is infected with influenza, they have a look at the timing of pneumococcal inoculation. So the mouse is infected on the day 0, and what's happening when we inoculate on the first day, on the second day, or the third day, etc. So for the first days, you can see that it's clearly the same as without influenza. Immediate clearance, eventual clearance, and invasion for high dose of inoculation. But after the second days, there are more possibilities of invasion, and on the 5th days, it's invasion is really, really probable. So the 5th days is very rare to be. The chance to have the bacteria just on the 5th days after infection is not very high, but when it happens, it can be very dangerous. So then they focus on this 5th day, and they have a look at, so the pneumococcal is inoculated on the 5th day, and they have a look at what's happening when we give antiviral treatments on the 1st day, the 2nd day, the 3rd day, etc. So what they show is that when we give the antiviral treatment early, so one, first, second, and third days, then the effect is nearly like if there were no influenza. But if we delay too much the treatment and we start treated after around the fourth day or after, then there is no effect of the treatment. So I think that's very interesting. Also, the treatment might not be very efficient at reducing the flu symptoms. If it's early, it can reduce severe complications. So it's a start in the direction of public health application, I think, to this interaction. So the third case study is the modeling and estimation of interaction at the population level. So that's a work we've been carrying out from surveillance data in France, from pneumococcal meningitis and respiratory viruses, and we build mechanistic models and feed them to population data to assess the interaction mechanism. So we are focused on pneumococci, and we develop a model of pneumococcal colonization. So the people can transmit the pneumococci, but it's asymptomatic. And then sometimes people can develop severe infection, and it's very rare, but it can happen. And then we introduce into this model some mechanism of influenza bacteria interaction. So here beta 0 is the natural pneumococcal transmission rate, and P0 is the natural chance to develop a meningitis for a pneumococcal. And then we introduce two mechanisms, one that is on two interaction mechanisms, one which is on the transmissibility of the bacteria. So the transmissibility of the bacteria can be affected by the virus incidence, and another one which is on the pathogenicity of the bacteria, so the chance to develop a meningitis, that can be affected by the virus incidence. And we test different models to see which of them can actually fit to the French data. And so we found that so from the 2001-2004 data in France, so before the introduction of PCV vaccine, we found that the best model was actually the one that included the two mechanisms, the one on transmission, so the virus would increase the pneumococcal transmission, and the one on pathogenicity. The virus can increase the probability of developing a severe infection in colonized individuals. So now we are extending this model to take into account several important factors for influenza or for pneumococcus, the age of the individuals, the type of virus for influenza, and type of respiratory viruses, RSV, etc., and the PCV vaccines. And we are analyzing the French pneumococcal meningitis over a longer period, and we are also trying to have to work together with Mark and people here to analyze the UK data from this model. So the final aim will be really to estimate the interaction and then to be able from a good model of interaction to assess the combined impact of different control strategies like antibiotic strategies or vaccination campaigns for pneumococcal or for influenza. So conclusion about this. There is very little has been done in terms of modeling flu interaction, and very little or nothing has been done in terms of using such models to predict the public health impact of control measures. I think the main challenge is to be able to model the multiple pathogens in interaction, because it's very hard to translate from a single host with natural history of the disease for influenza and natural history of the disease for another pathogen and timing in the interaction maybe to a population. So one possibility is to use some individual-based modeling. So in the lab, Hélène Ardouin has been developing an individual-based model of influenza in interaction with other pathogens. So this methodology allows to describe really precisely the natural history of each of the pathogens, and also to include this timing maybe in interaction and specific interactions. So this is just an illustration of simulations of different influenza outbreaks, and here it's pneumococcal, which is in interaction with influenza and the output in severe infection. And here is some simulation of two interacting viruses, or at least seasonal pathogen. So in terms of perspectives, I think it's obvious now that we have new technologies that allow for testing several pathogens at the same time with the multiplex PCR. Also, we have more and more information about the microbiota with all the metagenomic data, and more individual data of co-infection will become available in the future. So it's time for us to develop the tools to analyze this data. So we need to, there are lots of things to do because nothing is done. So we need to develop pathogen-specific interaction models. This model should allow us to characterize the interaction, so test hypotheses to identify the interaction, estimate the strength of interaction and the burden, and then to apply this model to public health, because I think that the next step will be really to have a broader perspective when we try to predict the impact of antiviral prescription, different vaccination or against viruses or bacteria, and take into account the pathogens that are also around and can increase or decrease as a consequence of the measure. So this is all the collaborators on this study, and I thank them all, and I thank you very much for your attention.
Apology if my question is very naive. What do you mean by interaction? Is it interaction as what we interpreted in the statistical term, which is the effect of the one intervention can change by the treatment? Or it is something else which I have no idea?
So when I talk about interaction, I'm actually talking about the biological interaction. So a biological mechanism that would make that one pathogen can impact the invasion or the colonization of another one. So it's maybe it's not the best term for that, but yeah, that's what I mean.
Thanks, Lou. That was really interesting. Is that working or do I shout?
I can.
Is that working? Yeah. I mean, I'm sure there are interactions between. Oh, you've convinced me. But have you got any idea about the attributable fraction at all? Have you ever tried to estimate that? What fraction of, say, pneumonia cases might be as a result of interaction with influenza, or the other way around, or?
So that's a very good question, and actually that's one of the things I've put in the list of the things we should do. So as I was mentioning, so this has been done for the interaction between pneumococci and influenza. This has been done mainly from some statistical analysis of the surveillance data. Actually, the burden was not so high from these studies, but also the studies couldn't find very high interaction level in the statistical analysis. So I think the question is really, does that regression method based on time series analysis are really the best method to analyze this data? And actually, is surveillance data the best data we can use to study interaction? And I think that now, if we can have individual data of co-infection, maybe we will be able to estimate better the burden. And but also, I think for pneumonia, maybe it's not really the case, but for meningitis, for example, if you can avoid maybe 10 or 20 cases a year in our countries, I think it can. That's not a number that is not, that the public health policies can listen to. Yeah. Sorry.
Hi.
Oh, sorry.
I just wanted to add to the question about how do you understand the interaction. So in a very naive way of thinking of the interaction between the pathogens, are you suggesting making a use of a epidemiological knowledge, like, for example, a model that would have different types of pathogens, because the problem with that would be how do you define if there are different high-risk groups, for example, for different pathogens? Or are you talking more about evaluating an overall impactfulness of strategies where there is an interaction between pathogens, if that makes sense?
Yeah, I mean, I think they can both answer to the question. If I understand well the question, I would say that both can help in understanding better the question of interaction and impact of vaccination, for example.
To do it with a large model, because is that how you're suggesting, to kind of include looking at incorporating data from different surveillance studies into a large model that has pneumonia and flu viruses?
Yeah.
Okay.
So I think, well, I mean, what we are doing at the moment, so is it more a question about the modeling or about the epidemiological setup? Yeah. Yeah, if you want to set up an epidemiological study, you can, I mean, you were mentioning who are the at-risk people, for example. I think you want to see, you can have a group of people that have influenza and people who don't have influenza, and have a look in these people who have influenza if they are more colonized with the bacteria, for example, and in the people who are colonized, if the risk of otitis, sinusitis, pneumonia is higher. For epidemiological studies, I think it's, and when you do that, you can even have a look at more pathogen than only 2. When you do a model, I think we can start with 2, maybe, because, from the methods that were presented by Anne this morning, the evidence synthesis, you can bring data from different sources, and the idea is really to try to estimate the unknown parameters and compare different hypotheses in different models and see which are the one who actually fit better to the data.
Ian Choi from Collindale here. Thanks for the nice presentation. A lot of people are aware, there are many different types of influenza, but also there are more than 90 serotypes of pneumococcus. And after the PCB 7, 10, 13 are being introduced in many countries, this vaccine introduction actually altered the epidemiology of pneumococcus. So how are you going to cope with this big perturbation?
Yeah, I think it's a very good question, because if there are actually interactions between pneumococci and influenza, I believe there are, and some others believe, but maybe they are not so. It might depend on the serotypes, because there are many differences between serotypes. You don't see the same serotypes in children and in adults, for example. You don't see the same serotypes in carriage and in infection. You don't see the same in otitis and meningitis. So, yeah, there are lots of differences between serotypes. And also the different age groups are not infected by the same viruses. So I think the first thing maybe would be to have a look at the age. And we would like to find a way to group the serotypes according to some specificities, maybe virulence or something like this. It's impossible to do a model for each serotype, but trying to group them, the serotypes you find in meningitis and the one you never find in meningitis that are only carried, doesn't make sense really to. And another thing we really want to do is to include in the estimation framework some carriage data, because I think it will make a big difference.
Thanks again, Lulla. And so now we will have the last talk before having the discussion. So the last talk is Katie Atkins from the London School of Hygiene and Tropical Medicine, and she's going to present how actually you can use this model to talk with policymakers and